Now that we know how to draw resonance structures, let's look for some patterns of resonance structures. So our first pattern is when you see a lone pair of electrons next to a pi bond, right? So this blue lone pair of electrons next door to this magenta colored pi bond. So what we could do is we could show the movement of this lone pair of electrons into here to form a new pi bond, and we can't leave the structure like that because that would have carbon violating the octet rule, as we saw in our last video. So we need to move out these magenta electrons onto this top oxygen here, and let's see what the resulting resonance structure would look like. So let's go ahead and put in our sigma bonds here like that. So this oxygen had a lone pair like that, and we showed the movement of the blue electrons in here to form a new pi bond, and our magenta electrons from our old pi bond now moved out onto this top oxygen here. So this would be the resulting dot structure. Well, since these two are resonance structures, we need to put in our resonance brackets, and we have to assign our formal charges. So this top oxygen here, one bond, 3 lone pairs of electrons, that gives it a -1 formal charge. So again, watch the videos on formal charge if you need some help with that. Our bottom oxygen, right, 3 bonds, 1 lone pair, giving it a +1 formal charge. So those would be my resonance structures for this molecule. Our next pattern will be a lone pair of electrons next to a positive charge. So if I look at a lone pair of electrons next to a positive charge, I'm going to say my positive charge is on that carbon, so it's a carbocation, and my lone pair of electrons is on that nitrogen. So this is an easy one, right? The goal is to spread out that positive charge throughout the molecule. So how could I show the movement of electrons to delocalize that positive charge? Well, all I have to do is show the movement of that lone pair of electrons in here to form a new pi bond. So let's see what that would do to my structure, right? So now I would have a situation like this. And what happened here? Well, let's move in my magenta electron. So that has formed a new bond, right? A pi bond between that nitrogen and that carbon. So this carbon here gained a bond, right? So now it no longer has a +1 formal charge. Where did that +1 formal charge go? It went to the nitrogen, because nitrogen now has 4 bonds around it with 0 lone pairs of electrons. So we have delocalized that positive formal charge and helped to stabilize the molecule like that. Let's look at our next pattern, which would be a pi bond next to a positive charge. So if I take a ring again and I put 2 pi bonds in there, and I'm going to say that this carbon is positively charged. So what could I do to delocalize that positive charge? Well, whenever I see a pi bond next to a positive charge, I could move those pi electrons to move around that formal charge. So if I move these pi electrons over here, right, I add a bond to this carbon, so I get rid of that +1 formal charge. And I take away a bond from this carbon up here, so that's where my formal charge will go. So let's draw what happens, right? So I move those 2 electrons over here. The formal charge disappeared from this carbon. It moved up here to the top carbon, so that now gets my +1 formal charge. I have the same pattern, right? I have a pi bond next to a positive charge, so now I could show the movement of these pi electrons in here to form a new resonance structure and to move around that positive charge even more. So what would I get, right? Well, I took a bond away from this carbon this time, so this carbon is going to get my +1 formal charge. So I can draw a total of 3 resonance structures to delocalize that positive formal charge. Our next pattern will be a pi bond between 2 atoms that have different values for electronegativity. So if I show a carbonyl bond, right, a carbonyl between my oxygen and my carbonyl carbon, I know oxygen's much more electronegative than carbon. So oxygen wants the electrons more. So I could think about moving these pi electrons off onto my oxygen atom, and let's see what would result from that, right? So if I draw my resonance structure here, I'm only concerned with the movement of pi bonds, so I'm not going to touch my sigma bonds there. So my pi bond electrons moved out onto my top oxygen, so now this is my resonance structure. I must put in my formal charges. So if I if I assign formal charges, I think about, you know, this carbon right down here. It had 4 bonds, so 0 formal charge on the left, but it lost one of those bonds on the right. It only has 3 here. So now this carbon is positively charged, right? It's a carbocation. And the top oxygen, if you assign formal charges to it, it gets a -1 formal charge. All right, let's look at a similar example. It's actually the one we did in the last video, our first resonance structure. So if this was the situation for the first resonance structure that we drew, I went ahead and showed these electrons in blue, and I showed the pi electrons in magenta here. And if I do the same thing I did in the previous example, I say, oh, okay, I have a situation where I have atoms with different electronegativities. So I could move, you know, these pi electrons off onto my top oxygen. So let's see what I would get from that. Well, I forgot to put my negative charge in here on my oxygen, so make sure to put all your formal charges in like that. So let's see, what would result from the movement of those pi electrons? So let's see, the bottom oxygen still has 3 lone pairs of electrons around it, giving it a negative formal charge. So let me put in the last lone pair in blue there. And the magenta electrons have moved up here to the top oxygen. So it's the same situation as before in terms of formal charge. The top oxygen gets a negative formal charge, and this carbon lost a bond, so it ends up with a positive formal charge like that. So far we have 2 resonance structures, or we think we have 2 resonance structures so far. In the previous video, we were able to draw another resonance structure by taking these blue electrons and moving them in here to form a pi bond. So this is definitely a resonance structure because this gets rid of 2 formal charges at once. So let's see, what do I mean by that? So let's go ahead and draw in all of those lone pairs of electrons. The blue electrons have moved in here to form a new pi bond, and I still have a negative formal charge on my top oxygen there like that. But by moving those blue electrons in to form a new pi bond, I get rid of 2 formal charges, right? This central carbon here now has 4 bonds around it, so it has a 0 formal charge, and this oxygen also lost its formal charge. So this is very, very favorable for this resonance structure to happen. In general, if you're talking about which one of these 3 resonance structures are the most significant ones, which ones contribute the most to the overall resonance hybrid, you usually want to think about how can I minimize formal charges. So usually 2 would be the maximum number of formal charges that you could have for a resonance structure. So that must mean that the molecule on the left is okay because it has only 1 formal charge. The molecule on the right is okay because it has only 1 formal charge. But the resonance structure in the center has 3 formal charges, which destabilizes the molecule, right? You're trying to get rid of formal charge and delocalize it. So this is not a significant resonance structure. It does not contribute to the overall hybrid as much as the other 2. So the 2 on the ends are the significant resonance structures. Let's draw some more resonance structures. Let's do resonance structure for nitromethane. Okay, so we assigned formal charges to nitromethane in the formal charge video, and let's go ahead and see if we can use those formal charges to draw a resonance structure for nitromethane. So let me go ahead and put in all of my lone pairs of electrons on nitromethane, and let me show this double bond of this nitrogen to that oxygen there. So formal charges, right? We've seen that this oxygen is negatively charged. This nitrogen has 4 bonds to it. It is positively charged. So what can I do to spread out those formal charges and delocalize it and stabilize the molecule? Well, I look for patterns, and I see a lone pair of electrons next door to a pi bond here. So I could say I could draw a resonance structure for this. I could move in that lone pair in here to form a new pi bond. And if that happens, I can't leave the resonance structure like that because nitrogen would have too many electrons around it. Nitrogen would violate the octet rule, and being in the second period, nitrogen can't violate the octet rule. So at the same time, I must kick off the electrons in this pi bond onto that top oxygen there, and let's see what would result after all of those electrons move like that. So now I have, let's see what I have here. I have my bottom oxygen, and let me just clarify where those where those are going to go here. So let me just eliminate those electrons and let me redraw them real fast over here on this side. So my electrons go right here. My blue electrons had moved in here to form a new pi bond, and my magenta electrons had moved off onto my top oxygen here. So the formal charges, now my top oxygen has a negative formal charge. My nitrogen here has 4 bonds around it, so it still has a positive charge, and the bottom oxygen has a 0 formal charge. So the negative charges are actually delocalized, throughout that portion of the molecule there due to my resonance structures. Let's do a little bit more complicated one. Let's do nitrobenzene. So let's take our concept of a nitro group and let's apply it to a benzene ring as well. So I'm going to go ahead and put my lone pairs of electrons in here, and that is what my nitro group looks like. A negative charge on my top oxygen, right, and a positive formal charge on this nitrogen. And I'm going to attach this to a benzene ring to make nitrobenzene, right? So let's go ahead and show that. So this would be nitrobenzene with a benzene ring. Well, what could I do to delocalize those electrons? Well, first thing I could do is I could look for patterns, and I'd say, oh, well, here I have a pi bond next to a positive charge, right? So I could move the electrons in this pi bond in here to attempt to get rid of that formal charge. And if those electrons move in here, then on my oxygen, in the bond between oxygen and nitrogen, those electrons must kick off onto the oxygen because nitrogen cannot violate the octet rule. So let's see what kind of a resonance structure I would get, right, if those electrons moved in there. So the pi electrons move into this bond. So now I have this situation. The electrons in the pi bond between nitrogen and oxygen have moved off onto this top oxygen here. So now it has 3 lone pairs of electrons, and the oxygen on the right still has 3 lone pairs of electrons. And I still have my pi bonds over here and over here that have not changed. So what are my formal charges in my molecule? Well, my nitrogen has 4 bonds around it, so it gets a +1 formal charge. My oxygens are both negatively charged. And I took a bond away from this carbon, right? So this carbon will get a positive charge as well. So I have four formal charges in the molecule, and you would think that this would destabilize the molecule because, remember, I'm trying to minimize formal charges, so significant resonance structures, usually there's no more than 2. But because of the fact that my nitro group already had 2 to start with, this is an exception to that rule. So this is a significant resonance structure, even though it has more than 2 formal charges on it. I can draw another resonance structure because I see the same pattern, right? A pi bond next to a positive charge. So these electrons can move in here to attempt to delocalize that positive charge. And let's draw what would happen if those electrons move in there, right? The top part of the molecule stays the same. And to save time, I'm not going to put in my lone pairs of electrons in anymore. I'm just going to draw my formal charges, and the electrons are implied. So this pi bond is still here, and this bottom pi bond has moved up to here, and that adds a bond to this carbon, right? Adding a bond to that carbon takes away that positive charge. Where did that positive charge move? It moved to this carbon because that carbon lost a bond to it, so now that carbon is positively charged. And again, four formal charges, but this is a significant resonance structure. I can draw one more resonance structure because I see the same pattern of a pi bond next to a positive charge. So I can move those electrons from that pi bond over here, and let's draw the resulting resonance structure, right? So let me just go ahead and real quickly put in the top part of my molecule with 2 negative charges and a positive charge on my nitrogen, right? This pi bond stayed there, and this time the pi bond on the left moved over here to form a new pi bond right here. So what happened? Where did I lose a bond, right? Well, I gained a bond right here. That gets rid of that positive formal charge. And I lost a bond right here. So that is where my new formal charge is, like that. So those are my 4 resonance structures for nitrobenzene. And even though several of them have more than 2 formal charges, they are all significant. So these all contribute to stabilize the molecule.